Okay, so last topic is real-time scheduling or real-time systems. So I'm not sure if any of you have had this experience yet, but when you run code on Linux or Windows, the execution time varies between runs. You run the same code multiple times, and you get a different execution time every time, and it can be quite it could vary quite a bit. And operating systems like Linux and Windows don't have any mechanism to guarantee that a task will run in a certain amount of time. If they did, they would be a real-time operating system, but they're not. So the problem, though, is if you're designing a cyber-physical system or any kind of controller, like the one that we talked about in control when we talked about control theory, there was that T sub S, that's the time step, that's the controller time step. Anytime you make a discrete control system, you need to have a time step. You design it for the time step. And then when you execute that controller code on a CPU, you have to guarantee that the controller will execute within that time step every time it's invoked, right? If not, the control system can become unstable and act unpredictably. But yet, there's no operating system, or very few operating systems, that make any kind of guarantees like that. So for example, if I design a control system and I design it in the Z domain or I design it in the state space, and I have to set a time step value on there, and then I can do some analysis to ensure that the controller system is stable, but then I go to run it on Windows or Linux and it doesn't honor the time step. It doesn't execute because of uncertainties in the execution time. And so that's a problem. It gets even worse if you have a system where you have multiple control loops running on one processor. And they may even have different time steps. They may have different scan cycles or controller periods, whatever you want to call them, right? So I was mentioning that, like if you run a program on Linux and you run it over and over again, you time it, you'll get a distribution of execution times. And that distribution will look different for different codes. Usually when you do this, you're running code that follows one control path, right? So like obviously if you have code that has an if statement in it, and it does one thing on one input and does something else on another input, you would expect that execution time to vary depending on the inputs that you give it. But on the other hand, if you're running like just a feedback controller, right, that's just doing a predictable set of calculations that that it's the same calculation regardless of the data, right? Like for example, if you're doing linear algebra, for instance, that linear algebra routine will be the same workload, the same computational workload, regardless of what input you give it. You'll still get different execution times, and sometimes those execution times will be normally distributed. Sometimes they'll be exponentially distributed, but the execution time will be a random variable. And why is that? Well, there's reasons for that. There are hardware reasons for that, and there's software reasons for that. Hardware reasons for that would be things like cache misses and interrupts that you can't predict. So if you get an interrupt, the CPU has to execute an interrupt service routine, and it takes time away from the code that's running on the CPU. And you can't predict it. By their nature, interrupts are unpredictable, right? They can happen for, hardware events like a peripheral needs attention. You receive a packet on your network adapter, or they could even be a regular timer, interrupt, right? A timer interrupt, but that timer interrupt may not be operating on the same frequency as your control. So, when you look at your execution time, it may still look like, you have random delays in there, random outliers in terms of the execution time, even if you have a timer that's executing at periodic intervals. So that's the reason, and of course in the software sense, if you have an operating system like Linux, it's going to have a scheduler that periodically executes, and sometimes that scheduler will decide to run another task on that CPU. that you were running, that your code was running on. And it's difficult to predict the behavior of the scheduler. Now, you would think that in the current era of multi-core CPUs, that wouldn't be a big deal, because if I have an 8-core CPU in my system, you know, what's the likelihood of the core I'm on executing an interrupt service routine, right? Well, it turns out it's very likely. It's very difficult to make that execution time deterministic, even, or predictable, even on a multi-core CPU. I know this from trying it. Now, Linux, to Linux's credit, they're trying to incorporate features in the kernel to make it more, to deliver more deterministic execution times, but it's far from being able to do that. Okay, so anyway, so the problem though is, what do? Like you have a code, you have a control system, it's designed with a discrete controller time step interval. I have to run it on a CPU. What do? Well, your goal is to measure the worst case execution time for your code. The problem is that because the execution time is a random variable, there's no way to find the worst case execution time. It's you know, if you have if you have data that's normally distributed, you know, you could have data points way far from the mean, right? It's unlikely, but you know, they will eventually happen, especially if this is a control system that's running for a long time, right? I mean, it's running indefinitely. It's an embedded system, right? It's controlling, you know, the autopilot in a plane, or it's controlling a robot, or it's controlling an arm. It's just running for a long time. So no matter how unlikely it is, you'll have one of these outliers. You'll eventually get one. So one way to estimate the worst case execution time, one of the things that people do is they fit the execution time to a distribution, and then they can calculate the worst case execution time with a confidence interval. So for instance, if the data is normally distributed, then if you take the mean and you go out to 3.09 standard deviations above greater than the mean, you can estimate that would be your worst case execution time with a 99.9% confidence. Right, that's one way that you can calculate that. Now, you can sometimes get a little bit more accurate if you understand what's happening. Like, this would be kind of a black box way of doing it. But if the code behaves different under different operating modes or different inputs, then you can model the execution time as a mixture of distribution. So in this case, it's just the same data, but now I'm using a little bit of insight into what's going on to say that there's actually 3 different execution paths that are taken when you execute the code, and I can model each one of those as a separate distribution, and then that way I can get a tighter bound. You know, even though I have this one mode that's way over here at 40 milliseconds. I can calculate the worst case execution time for each one of these with whatever confidence I want, and then just take the max of those, and I can get a tighter bound. So here's an example of that. Okay, so let's assume that we have a task, and we run it 10 times, and we get the following execution times in milliseconds. And so the question is, what is the worst case execution time with a 99.9% confidence interval? So we just calculate the mean of those values. So the mean of all these is 20.5 milliseconds, and the standard deviation is 9.2. And so the worst case execution time with a 99.9% confidence is the mean plus 3.09 standard deviations from the mean, which is 48.9. Now you can see that, now you might look at that and say, wait, well, hold on, 48? There's nothing in here anywhere near 48, right? I mean, these are all, the highest observation we saw was 32, right? But you have to assume that the worst case is 48 based on those samples. However, on the other hand, let's assume that the first 5, so 12, 13, 10, 14, 11, let's assume that these are from one operating mode of the code, and the second 5 are from another operating code. And you can see that the first 5 are sort of lower, than the second 5, right? And so if you do it that way, you can calculate both means. So the mean of the first 5 is 12 and the mean of the second 5 is 29. And then you calculate the standard deviation of the first 5 and the second 5. It's 1.6 and 2.9. Now, because the standard deviation is so much smaller when I just consider, the first group and the second group, right? That way I can calculate the worst case execution time of the max of the first mean plus 3.09 standard deviations and the second mean plus 3.09 standard deviations. And that gives me, I'm choosing a max between 16.9 and 38, so 38. So 38 is less than 48 because I was able to more accurately, model the execution time using, some insight into the code as opposed to just, looking at it, the execution times by themselves. Okay, so once you do that, once you have an idea of how long it takes to run a task, you have to consider how an operating system is going to schedule that task to run. So each task in an OS is generally going to have three states it's in. It's either ready, meaning that it's ready to be executed, but it hasn't been executed. It's basically it's kind of holding, waiting to run. Or it could be asleep, meaning that it's completed execution time. And usually with a real-time operating system, generally tasks run to completion and they run again sometime later and then again and again, right? Because the code is designed to be controlling something, right? Or you could be executing, right? So let's assume now that we have 4 different tasks, because a lot of, like if you think of your car's computer, you got a lot of, chips in your car, but each chip may be running multiple things. You're not going to have one dedicated processor core for every controller. So let's assume that we have 4 controllers or 4 tasks, and they have different execution times, and they have different deadlines. So this is the, when they need to complete execution. So, obviously the computation time or the execution time, worst case execution time, is going to be less than, their deadline, obviously, otherwise it would be impossible from the start. And in some cases, you've got quite a nice buffer there. Like, for example, this guy only takes 6 milliseconds, but he only needs to be done by 84 milliseconds, right? Other ones are a little tighter, right? So this one's got 20 milliseconds and has to complete by 37 milliseconds, right? And so it turns out that even if these tasks just execute once, there are 4 factorial different ways that we can run them to completion, right? Different orderings, right? So there's 24 ways that we can run. And if we look at all 24 of these orderings, and I'm showing them here, like I'm assuming, again, there's 1 core, so I can only execute 1 task at a time. So at any given time, one of these tasks will be running, which is indicated by, a 1 here, right? So you got a 1 and the others are 0. So in this case, we run task 4 first, and when it gets done, which will get done at 20 milliseconds, then we pick up task 3, and when that gets done, we pick up task 2, and when that gets done, we pick up task 1. So the order we run these is 4, 3, 2, 1, and then I show the deadlines here as these little red lines, right? And in that case, we actually meet the deadline on task 4 and on task 3 and on task 2, but we blow past the deadline on task 1, right? So that one won't work. In the second case, we execute task 4, task 3, then task 1, then task 2, and that one actually meets all of its deadlines. But then we try the same thing with 4, 2, 3, 1, and that misses the deadline. And you look at all the rest of these combinations, and in fact, all of them miss their deadline except for 2. So only 2 out of 24 meet their deadlines. So I've got them all shown there. Okay, so it turns out, though, that the 2 that met their deadlines actually were scheduled according to two possible scheduling policies. One of them is earliest deadline first. So if you choose the order based on the earliest deadline, so the earliest deadline is task 3, then the next earliest is 4, then 1, then 2. So if you do 3, 4, 1, 2, that's fine. That meets the deadline. And for there's another approach called least slack first. So slack is the difference between the deadline and the execution time. It's the amount of cushion you have. And so we calculate the slacks for all these guys, and the one with the least amount of slack, which is the tightest deadline, is 4. So we run 4, and then 3, and then 1 and 2. And that one is the second one that met its deadline. Another approach is you could run the shortest task first, in which case you would do 2, 3, 4, and 1, right? Yeah, 2, 3, 4, and 1, but that one doesn't work. That's one of the ones that misses the deadline. Specifically, we miss it on 1 and 4. So 2 of these tasks miss their deadline, right? So it's not real straightforward to figure this out. As you can imagine, if you have more tasks, it becomes harder. However, even what I showed there is kind of a simple case, because this is non-periodic. I didn't relaunch each task after its deadline expired, but in reality, that's what's going to happen in a control system. A control system will have a time step, and then after the time step expires, it needs a relaunch. And so they're periodic. Every T sub S, they need to invoke the control. And so in this example was not periodic. They ran once and then they were done. This is more of a traditional approach. But in a real-time system, you have to run, the deadline and the repetition interval are the same, right? Period, right? So let's assume now that we have one CPU again, and each task has an execution time and a period. Okay, so the period is now the deadline. So these numbers are all the same. So the execution time is the same. It's the same for tasks, same for execution time. The only difference is instead of deadline, I just call it period, because I assume that at that period, not only is it a deadline, but they have to, run again, right? Okay, so now we can also assume, unlike before, that we can add another ingredient here called preemption, which means that you don't necessarily have to run a task to completion. You can start a task running, and then you can tell it to chill for a while and let another task run, and then we can go back to the original one, right? So preemption just means that once you start running, you don't have to finish. You can give it a little time on the CPU and then take it away, right? That's preemption. And so we want to find a schedule where no task misses its deadline. And so the first thing you want to do when you want to do an analysis of this is calculate the utilization. So the utilization is the sum of all the ratios between the calculation time and the period. Because the idea here, unlike the previous example I showed you, is that after the deadline expires, we need to run again. So every period, we assume that we have to run that task for that portion of the period, right? So we call that the utilization, but then you have to add all the utilizations up. And the sum can't exceed 100%, otherwise it's impossible. So in this case, if I calculate the utilization, which is 40 over 76, plus 6 over 84, plus 14 over 35, plus 20 over 37, the total is actually 1.5383, which means that there's no way, it doesn't matter, there's no possible way I could ever schedule this, because it would require 153% of my CPU. Okay, so for periodic preemptible scheduling, there are two kind of baseline scheduling techniques. These are kind of the most widely known. The first is called earliest deadline first, which is where you schedule the task with the earliest deadline. Okay. Now the problem with this, now you might think, well, that's pretty common sense, right? I mean, you did that before, right? I did this with earliest deadline first. I did it here, right? All I had to do was find the earliest deadline, and that was the order, right? Simple. But it's not so simple in a periodic sense. This wasn't periodic. So the deadlines were very easy to calculate. All I had to do is look at this deadline column, and I'm done, right? I just sort by this. But the problem is, with a periodic task, The deadline for a task is how much time you have to the end of its next period, right? And you have to keep in mind that you might have a task running and another task becomes ready because it starts its new period, right? And the minute it becomes ready, it may already have an earlier deadline than something that's currently running. So the problem with earliest deadline first is that you have to constantly recalculate the deadlines because tasks are constantly coming up. You know, they're coming up to be ready at the end of their periods, and their periods are all out of sync from one another. They're all different periods. They're not. So what you end up with is that if you look at all the periods, unless they're harmonic, and usually they're not, if the periods are not harmonics of one another, then you have a very sort of chaotic pattern. In fact, you don't really have a pattern at all. It's kind of, you know, when each new task starts and who has the earliest deadline at any time, right? So that's one approach. A simpler approach is called rate monotonic scheduling, which is where you just schedule tasks with the shortest period first, okay? Now, you still have to preempt, you know, like if a task becomes ready and it has a shorter period than the one that's currently running, then it will preempt the one that's running, right? But the advantage of rate monotonic scheduling is that the determination of who has the highest priority is static. It's basically you look at all your ready tasks, right? And whichever one had the shortest period, that has the highest priority, right? It's very simple. Whereas with earliest deadline first, you have to look at all your ready tasks, and then you have to look at the current time as compared to the next deadline for all the tasks, right? So you have to recalculate. You have to do a calculation of all the deadlines every time a new task becomes ready, right? Whereas with rate monotonic, there's no recalculation. You just say, okay, who has the shortest period? You get the highest priority, right? So that's the main difference between these two. Now you might say, okay, well then why would anyone use EDF scheduling, right? Well, it turns out though that EDF is better in terms of how high the utilization you can achieve, right? So let me give you an example of this. So with earliest deadline first, let's say now we have 3 tasks, and this one is going to be more reasonable set of tasks than what we had before. There's 3 tasks, 10 milliseconds, 40, 15, 50, 5, 20. If you calculate the utilization of this set, it's 10 over 40 plus 15 over 50 plus 5 over 20. It's 80%. So you would think that, that should be okay, because this is an 80% utilization. I should be able to schedule this without missing any deadlines on these guys. So you start out, this is earliest deadline first, so the priorities are calculated as the period of that task. So each task period, each task priority is that task's period, minus the current clock cycle or time modulo its period, right? Okay, because you have to figure out where you are within the current period and subtract that from the period to figure out how much when the deadline is from the current point of time, right? Make sense? Relative to the current time, right? You're calculating the period relative to the current time. So when you start out, all 3 tasks are ready. Task 3, I put red markers here to show when each task begins. So they all begin at the same time. Task 3 is, you know, the earliest deadline there because its period is 20. So naturally it gets the highest. Next is task 1 and then task 2. So I run all 3, no problem. Task 3, in fact, task 3, it always will preempt whoever's running whenever its period starts because it has the smallest period, right? But it gets complicated because if you look at this, task 1, it meets its deadlines, but task 2 has got the longest period and the shortest execution time. And look at the weird, it has a weird kind of, check this out. And I didn't do this by hand. I wrote a program that generated this plot. So this is, unless I have a bug in my code, this should be correct. So task 2, you see it gets preempted here, and then it runs the completion. It gets preempted here, it runs the completion. But then here, oh, it didn't need to be preempted because it just happened to fall on a span of time where it was the highest priority. So it actually got to run without being preempted, but that only happened in its third period, right? And then here it got preempted in a weird way, right? So the point here is that because these periods are not harmonics of one another, you get some strange patterns, but it turns out none of them miss their deadlines, right? So no problem. Okay, but then we try rate monotonic scheduling. So in this case, again, task 3 is always going to run whenever it begins because it's got the lowest period. And then the next lowest period is task 1, meaning that task 1 will always run as long as task 3 is done. As task 3 is done for its period, in other words, it's asleep, then task 1 will get that next highest. And then task 2 is going to have the lowest period, and you can see again it has this weird pattern with preemptions. So it looks like, I think in this case they all do meet their deadlines, right? Yeah, we don't miss any deadlines here, so we're okay, right? But the question is, for these EDF and RMS, can I always guarantee that I can schedule them, regardless of the utilization, as long as it's less than or equal to 100%? Oh, here's another one. Okay, so here's another example where another 3 tasks with a utilization of 98.3, EDF schedules it, RMS fails. So RMS misses its deadline here on task 3, even though it was less than 100% utilization. So as it turns out, EDF is optimal in the sense that as long as the utilization is less than 100%, you will be able to schedule a periodic task set, assuming you have a preemptible scheduler, and assuming, of course, that you have 0 scheduling overhead, which is also kind of an unrealistic assumption because the scheduler, especially with EDF, because you have to recalculate all the priorities constantly, right? Which is why, generally speaking, it's not feasible to use EDF. I don't think I've ever seen a real-time operating system that uses EDF. It's just not, it's not practical. For RMS, which is practical, there is a schedulability test that you can do to determine ahead of time whether or not you can guarantee that it can schedule. Now, the crazy thing about this test, though, is that this test, if you pass this test, it guarantees that you can schedule your tasks. If you fail the test, it doesn't mean that you can't schedule it. It just means, I don't know. I don't know if it can be scheduled. Unclear, right? And as it turns out, when I was in and this is a crazy, when I was in grad school, I took a real-time systems course. And at that time, this was in 2000, I think, 99, 2000. When I took that course, the schedulability test for RMS was different because at that time, the best understanding of it was that as long as the utilization was under 69%, you can schedule. It was just a fixed number. That was called the Liu and Leyland bound. It was these 2 guys wrote a paper, Liu and Leyland, and that was what they derived. So they said if you're under 69% utilization, guaranteed RMS can schedule it, right? But now there's a different one because there was another paper and they have a tighter bound, right? But even this bound is not perfect, right? So the question is, this is basically an unsolved mathematical problem, which is how do you like, what is the ideal or optimal bound for this? No one knows. But this is the best one that's available now. So what you do is you take each task and each period for the task, and you say 1 plus the ratio, right? And then you multiply all those guys together. And if the product of all those is less than or equal to 2, then that means that RMS is guaranteed to be able to schedule it. And again, this is also assuming, an infinitely fast scheduler, right? Which is not the case because in reality, the scheduler is actually an interrupt that has to be called, and then the scheduler has to go in and figure out what to do. So there's overheads there. But even if there's no overheads, that's the schedule, that's the bound. So in this case, if I have these 3 tasks, if I take 1 over 40 times 15 over 50 times, 1 plus 10 over 40 times 1 plus 15 over 50 times 1 plus 5 over 20, I get 1.95. So this one is guaranteed to schedule, right? Of course, on this case, this set of tasks doesn't. It gives me 2.33 when I calculate this. So that fails the test, but doesn't mean that it can't be scheduled with RMS. We don't know. And you might say, well, hold on, man, just run it, try it. I mean, you wrote a program that evaluates this, did you not? I have a program right here that generated these plots that will literally simulate an RMS scheduler. Yeah, but how long do you run it for? Right? I mean, you have no, like, I could run this for a long time and I may not get any deadline violations, but how do I know that I can run it for an infinite amount of time and not have any deadline? This is just, this program, I can run this, but notice how over in this case, I didn't have my deadline violation until out here. Everything was fine prior to that, right? So you can't just simulate this. You have to calculate a bound mathematically for this. And by the way, I didn't show it here, but the utilization is less than 100, I believe. 4 over 10 plus 3 over 12 plus 5 over 15. So that's 0.4. That's 3/12. That's 0.25, right? So that's 0.65, and that's 1/3. So actually, that might be. I guess that's right over 100%. So that was a bad example. But you can have less than 100% utilization, but still fail this test. Okay, so now on the other hand, there are some corner cases here. If the periods are mutually harmonic, meaning that they're multiple, the periods are multiples of one another. So if I have my periods set at 20, 40, and 80, what that means is that the deadlines. Every time the deadlines will be aligned, essentially, right? If that's the case, then there was a proof that the RMS could schedule up to 100% utilization in that for mutually harmonic periods. But of course, the previous examples, that wasn't the case. Okay, so that's for one CPU, and that was the kind of the goal up until a few years ago, was to calculate these bounds and come up with these scheduling algorithms for one CPU. But as you might know, as I'm sure you know, most CPUs these days are multi-core, even the embedded ones that are in like the CPU that controls a solid-state disk has like 3 cores in it, right? So the question now is, how do you do this now on multiprocessors? How do I schedule real-time task sets on multiprocessor? This is a harder problem. So there's a couple ways to approach this. One way to do it is through partitioned scheduling, which is where this is the simpler approach. This is where you just say, okay, I've got a set of tasks, I've got a set of CPUs. I'm going to partition my tasks and assign each task only one CPU it can run on, right? So that way I treat this problem as basically I just do multiple single CPU schedulers, right? For each CPU set of tasks. Right? Now, that's one approach. The problem with that is, how do I assign tasks to CPUs? Well, it's basically random, right? As far as I know, there's no methodology for that. You just have to divvy them up arbitrarily. A better approach is global scheduling, which is where you allow any task to run on any CPU. So every time a task becomes ready, because its period starts, just like before, you have to decide whether or not you want to, preempt who is ever running and run it. Or sometimes you don't have to preempt. Sometimes the CPU is just idle, right? In which case you can, run. And if no one's ready, then the CPU will be idle. But normally, if a CPU becomes a task becomes ready because it's starting its new period, you have to decide whether you're going to run it or not. And with a multi-CPU system, you have to then also decide what CPU to run it on, right? So ideally, if I have 2 CPUs, in a perfect world, I would be able to schedule any task set with a utilization of up to 200%, right? Ideally. And if I have 3 CPUs, I ought to be able to schedule anything that has a utilization up to 300%. Unfortunately, that's not the case. It doesn't scale nearly that well. So one algorithm is called rate monotonic first fit periodic scheduling. And the idea is that you assign a task So as the state, you know, of the ready task changes, someone comes ready, you assign a task to the first processor that passes the single CPU RMS schedulability test with the other tasks that are assigned to it. Okay, so in that case, so how do we not forget? How do we know which one is assigned? How we assign? So this one is a scheduling test. This one is kind of crazy that you have to take. You add up all of the basically calculated utilization, which is the execution time over the period. You add all those guys up, and the utilization has to be less than or equal to not the number of processors, which in this case is M, but M times the square root of 2 minus 1, which is 0.41. So the total utilization has to be less than or equal to 0.41 times the number of processors. That kind of sucks. That's no good at all. I mean, ideally, you know, so that, I mean, but again, though, this is only a test to guarantee schedulability. Okay? So if you, like for example, if you have one CPU, and by the way, I mean, we're assuming that one of the things that we're hoping is that if we have multiple CPUs, there should never be a case where we can't schedule on 2 CPUs when we could schedule on 1, right? That wouldn't make any sense, right? That would be awful. So like for example, if we have one CPU and we have this task set, we calculate the total utilization is 76.5. If we calculate the traditional RMS, bound, it would be 1 plus 2 over 17 times 1 plus 2 over 19 times 1 plus 5 over 21 plus 1 plus 7 over 23. 23. Those are the execution times and periods of those 4. It comes out to be 1.9949, so it barely makes it, right? So we can schedule this on 1 CPU, but can we schedule it on 2? Well, for 2 CPUs, basically all you're doing is you're calculating the utilization bound, which is 0.41 times 2, right? Which is 0.82. So as long as the total utilization is less than or equal to 0.82, we should be able to schedule on 2 CPUs. And of course it is, because the utilization is 76.5. So we can put it on 2, right? So we can schedule on 1 or 2. Of course, what's the point of having 2 if we can schedule on 1? However, let's assume that you have this set of tasks, another set of 4 tasks that has a utilization of 78%. This one, if we calculate the traditional RMS bound, it's 1 plus 3/17 times 1 plus 2/19 plus times 1 plus 5/21 times 1 plus 6/23. When you multiply those up, you get 203. So it fails the single CPU schedulability test for RMS. But on 2 CPUs, it's fine because the utilization was 78, which is less than 0.82, which is our the 2 CPU bound. Right? Does it make sense? So the idea is you can also use earliest deadline first. That was basically, by the way, that was essentially the RMS, version of the multi-core RMS. Okay, so another approach is to use earliest deadline first. And so to do this, I try to come up with an example of this that is easy to follow. So at the beginning, we have, in this case, we have 5 tasks. So this one's a larger example, 2 CPUs this time. And at the beginning, all 5 tasks are ready. Now the periods I'm showing, the periods are color-coded. So I've got T1 is purple, and it has the largest period. In fact, it's so big it doesn't even fit. T2 is got a period of 20, so you can see that we've got two periods of T2, so the total time is 40. So this whole thing is the period of task 1, and we have 2 periods of task 2, and 4 periods of task 3, and 1 period of task 4, and task 5 is, it's not it's 15, and that one's green. Okay, so they're all 5 of these guys are ready, and so T3 has the lowest or highest priority because it has the smallest period. So we schedule that guy first. The next highest priority is who? It's going to be task 5, right? Which is a period of 15. So we'll schedule task 5. Now, in this case, task 5 had the second smallest period, but it also had a shorter execution time than task 3. Okay, so at this point, after task 5 completes, we need to recalculate the priorities. And I mentioned earlier that every time a task is ready to start a new period, you have to recalculate the priorities. But obviously, you also have to do that when a task ends, right? So there's 2 different events that would trigger a period recalculation. So T5 finishes here. We have to recalculate the priorities. Now, the ones that we want to look at are the only 3 ready tasks at this point: T1, T2, and T4, because we've had one task is running, 1 task completed, right? And there's only 3 left that are ready to go. So of those, T1 has a long period, T2 has a shorter period, and T4 has a long. So I think look, T2, right, is ready. So I'm going to put T2 on CPU 2, right? And then I have to recalculate my priorities after T3 ends. So T3 ends, at which point I only have 2 ready tasks, 1 and 4. They both have the same period, so I don't think it really matters. Pick one of them. So I'm going to pick T1. After T1 finishes, T1 just happens to finish at the same time that T3 is ready to go again, because he's starting a new period. So now I have T1, T3, T4 ready. So it looks like T1... See, I don't even know where we're at. Let's see, we're at the end of T3. So we're at 10. Our time is 10. So T1's deadline is going to be in 30 units of time. T3's deadline is going to be in 10 units of time because his period is 10. So I think T3 is going to have to go again, right? And T4 is also got another 30. So it looks like T3's got to go, right? So we schedule T3. Then at the end of T2, we just have T1 and 4, which are both the same. So I'll just run T1. Now, notice that T1 has a long execution time. So it was preempted here, right? And then we picked him back up here and let him finish to completion, right? And then T4 was ready after T3 finished, and unfortunately it didn't get the CPU for very long before it's going to get preempted when T5 is ready to go again. So T5 is going to kick him off, and then it'll finish, and then the only thing we have left there is T4. So we run that, but not for long because he gets preempted again when T2 becomes ready, right? So T2 is going to run, and so on, right? So that's basically the earliest deadline first multi-core version of EDF. The problem is that this one is not optimal like the single CPU one is. So if you have 2 CPUs, you're not guaranteed to be able to schedule with multi-core EDF as long as the utilization is less than or equal to 200%. It doesn't work that way. And in fact, the schedulability test for this one is pretty wacky. So the first thing you have to do is obviously you have to check to see if the utilization is less than 100% multiplied by the number of CPUs, right? That part's obvious. But there's a second condition. The second condition is that you have to calculate the greatest common divisor of the periods. Okay? And then you multiply the execution time of all of them, the greatest common divisor multiplied by the execution time divided by their periods. You do that for all of them. And if all of those numbers are integers, like no fractional part, then it's schedulable. Right? So for example, if I have in this case I have two processors, the greatest common divisor is 5. Right? Because it would have been 10, but I have this 15 here. So it's 5. So then I have to take 5 and multiply it by each of the ratios of execution time to period. And when I do that, I get 3, 2, 2, 2, and 1. So it's schedulable. Now, in this case, though, I've got a different set of tasks. So these periods are slightly different. You can see I got 16, 12, 16. So it looks like the greatest common divisor here is 4, because 4 divides all these periods. So I multiply 4 times the ratio of each's execution time to period, and you get some fractional numbers in here. And so this is not guaranteed to be schedulable. But again, it's not guaranteed. That doesn't mean it can't. We just don't know. We can't make a guarantee. And that's it. Those are the two algorithms. Any questions about that? So I mentioned that Linux and Windows are not real-time operating systems. There are very few real-time operating systems. They're virtually none. They used to have some variants of Linux that claimed to be, but not anymore. There are the only one I know that's a hard real-time operating system that's kind of well known is called oh gosh, I just lost it. I can't remember now. There is a company that claims to have one, but it's like $30,000 per seat. It's really expensive. There is a free one that's part of the Xilinx FPGA tools called FreeRTOS. It's very basic, and it's not really an operating system the way you would think of it. It's more of a library. You link your tasks into one executable, and then you dispatch that executable over bare metal, right? So it's not an operating system that has like a prompt, like it doesn't work that way. A real-time operating system is generally, just essentially an API that you compile into one executable. It's not interactive like a traditional operating system. But there's not a lot. In fact, the ones that even claim they're real time are not really real time. My colleague Austin Downey bought a so-called real-time operating system from LabVIEW that runs on an Intel Atom processor, and he measured it, and it's not. He gets that classic. He was doing a neural network which has a deterministic workload. Every time you give inputs to a neural network, it always does exactly the same number of calculations, same number of operations. But yet when he ran it over and over again, he got different execution times. It varied. So how do you really get real-time behavior? You guys know? I mean, the problem is even if you claim your operating system is real-time, as I mentioned, there are things inside the CPU. There are hardware factors, cache misses, and those kind of things, right? One thing you don't want in a real-time operating system is a virtual memory, because you don't want to ever have to worry about page faults. That's death to real-time, right? So that basically rules out using an Intel processor, because they force you to use virtual memory. At least an ARM processor or RISC-V, you have the option. You can use virtual memory or not, right? So how do you get real-time performance? Does anyone have an idea? Like if you really need real-time performance. The only way to do it is with an FPGA, hardware, a hardware design, where you can predict the execution time down to the clock cycle without ever having to worry about cache, interrupts, or anything else that could vary the execution time, right? Or an operating system, or any software in general is what makes execution time. Software is inherently non-deterministic in terms of its execution time. There's no way to get around that. If you really want to have a real hard real-time system, you have to use an FPGA and you have to write Verilog. That's the only way to do it. Which is why I cover it in this class, even though even though you might wonder, like, why is the hardware design? How does that have to do with control systems and real-time systems? That's what it is, and that's why when you look into a typical car, will have 40 FPGAs in it. Okay, well, that's all I have for this. So I think next lecture then we'll, just work in the lab unless you want me to do a review for the final exam. Final exam will be held during finals week. You can take it anytime you want. It's just like the midterm. It's 2 hours. Take it once. And open book, open internet. Just don't collaborate with each other. And then we'll be all finished. Okay? Sounds good. Thank you.